Okay, ma'am. See, there is x square plus a square. See, if it is about x square and a square combinations, there should be x square plus a square. There could be x square minus a square. There should be a square plus x square and a square minus x square. Right?
Yes, sir.
There are four varieties. Okay, this and this are same. Okay, so a square plus x square is inverse. That's why you got this, and this. There should be three. But here we have only these two. Okay,
Hmm.
that is an interesting thing. Okay, you will shortly notice why. Okay, similarly, if this is a square root, okay, square root you should have again this four. Square root of this, square root of this, square root of this, square root of this. Okay, these two are again match, so we should have this three. A square plus x square, a square minus x square. Okay, we should have this one also. Okay, minus x square minus a square. So basically, x square, a square, both positive, both negative. That's what we are doing. Okay.
Hmm.
So basically, we have these four, not these are anyway same. We have these four varieties. Okay,
Hmm.
but you can see here you have got only two varieties. Okay,
Yes, sir.
here you can see x square plus a square, x square minus a square, and a square minus x square. There are only three varieties. Why is the
Hmm.
fourth one missing? Right?
Yes, sir.
Okay, so here also a square plus x square, a square minus x square, and x square minus x square. X square. Only three varieties. Where is the fourth one? Okay,
Hmm.
so otherwise, if you take the permutations, you should get four, right?
Yes, sir.
Okay, why are we not getting the fourth one? Because, so for example, if you have to write a square minus x square and x square minus a square. Okay, so let's say dx by x square minus a square. This is nothing but minus of dx by a square minus x square, right?
Yes, sir.
Agreed. So that's why this actually means this is also covered. Okay. Similarly,
Hmm.
this one. This means minus of a square plus x square, right? Integral of dx by a square plus x square, which means this is also covered. This actually covers this. Understood?
Yes, sir.
Okay. Understood, no? So
Yes,
this
sir.
actually covers this one as well as this one. This covers this one as well as this one. Agreed?
Yes,
Okay.
yes.
So interesting. That is fine. But here you can see uh, here you cannot do that. What I am trying to say is a square plus x square. Okay. Here, here, there are only three types actually.
Okay.
We don't have minus a square minus x square here. See, do we have? We don't have, right?
No, sir.
In this one. But if you try to do minus of a square plus x square, which is not possible. Why? Because there is a square root.
Yes,
Okay,
sir.
ma? There is a square root because this is positive number, square root of a negative thing, which is not possible. That's why that is not there. Understood?
Okay.
In this case, we can actually modify and still be able to do. In this case, that is not there. That's why we have avoided the fourth type. Understood now?
Yes.
Okay. So now what you should tell me is now that you know a lot of these things, at least the first this part we have done. Okay.
Hmm.
Oh, kind of done. Okay. Now what you should do, you should tell me what exactly whose differential is this. We have done earlier. Whose differential? For now, let's assume that it is dx by x square plus 1 or 1 plus x square. Don't even complicate. Let's say a is 1. Okay. Now whose
dx
differential
by
is
1 plus x
x
square,
square?
sir.
Whose differential is whom if we differentiate, you will get 1 plus x square. We have done differentiations of what all? Trigonometric functions, inverse
Sine x
trigonometric
cube.
functions.
Sine inverse cos inverse.
So inverse trigonometric, and
Yes, sir.
hyperbolic, inverse hyperbolic. Okay. So these are six, these are six, these are six, these are six. Okay. Trigonometric functions, if you differentiate, you will get again a trigonometric function, right? Inverse trigonometric, if you are differentiating, you are getting functions in terms of x, right? So for
Yes,
example,
yes.
like this. And inverse hyperbolic also, we get something like this. Okay.
Hmm.
So you learnt a lot of differentiations: trigonometric, inverse trigonometric, hyperbolic, inverse hyperbolic. In that,
Yes,
you have
yes.
to search and find out and tell me Whom if you differentiate, you will get 1 by 1 plus x square.
Tan inverse x.
Tan inverse x, fantastic.
Hmm.
Whom if you differentiate, you get this one, let's say 1 by 1 minus x square. Just search and tell me.
1 by 1 minus x square, sir.
1 by 1 minus x square.
Cot inverse x.
Cot inverse or no, not cot inverse. That is 1 by 1 plus x square. You have to be careful. That's why I'm going little slow here, because
Hmm.
these completely understanding these differentials is very important. Okay, because this is dependent on this. This is also dependent on this. This all of these are later ones are dependent on these first four ones.
Okay.
Okay, so that's why let's go little slow. Also, 1 by 1 plus x square. You know it is tan inverse x. Okay. What
Yes.
about 1 by 1 minus x square? You just check all the six. Okay, you have six inverse trigonometric, six inverse hyperbolic. Be careful and check all the six. 6 plus 6.
Sir, tan h inverse x has 1 minus x square, right?
Very good. Tan h inverse x has got 1 minus x square. 1 by 1 minus x square. Right. Tan h inverse or cot h inverse. Okay. Now, now find out and tell me what is this tan h inverse x in terms of this is in terms of hyperbolic, no, in terms of the base functions, that is logarithmic and exponential. Can you tell me?
Base form.
So tan h inverse we did, right? We converted that into quadratic form. All the sin h inverse, cos h inverse, right? You remember
Hmm.
that? Okay. What exactly is tan h inverse? You remember this one? Tan h inverse. We did the we did all the inverse functions, right? See
Hmm.
here, this one. Tan h inverse x is half log 1 plus x by 1 minus x.
Hmm.
You remember this,
Yes.
no? What is cot h inverse x? Half log 1 plus x plus 1 by x minus 1. This is 1 plus x by 1 minus x. Why? Because x lies between minus 1 and 1. You remember the graph, no? Tan inverse x.
Yes, sir.
Okay, so tan hx, it lies between minus the y, the range is between minus 1 and 1, right? Tan
Yes,
h,
sir.
and that's why inverse is the domain is between minus 1 and 1,
Minus 1
right?
and 1.
You remember this, no?
Hmm.
This range is between minus 1 and 1. That's why this domain is between minus and 1. So that's why here it is one, the logarithm of this thing should be positive, no? That's why this is like this. And the next one is like that. Okay? X
Okay,
is
sir.
greater than 1. Okay? The inside one should be positive. Okay. So now you know, at least we have basic understanding that this we have touched upon somewhere, right? Previously.
Hmm.
While differentiating, we have faced this one, faced this one. Agreed?
Yes, sir.
Both tans, right?
Hmm.
This is also tan, this is tan H, this is normal tan. Okay? Okay. Now tell me, what about this one? 1 dx by 1 under
Root
root 1 minus
1.
x square. We have encountered this somewhere. Where exactly did we encounter?
Sir, sine inverse x.
Sine inverse x is what? Differential of sine inverse x?
1
Differential
by
coefficient?
root 1 minus x square.
X square. Very good. Fantastic. We have encountered this also somewhere. Under root 1 plus x square. So basically we are looking for some function which is something like this. This also find out where exactly we have encountered.
Yes, sir, 1 second. Sir, cosecant h inverse.
Which one you are talking about? X square
Well,
plus x square plus 1. X square plus 1 should be this one, no?
sine h inverse x, sir,
Sine
sorry.
h inverse.
Hmm.
Okay?
Yes, sir.
X square plus 1. What about we have encountered x square minus 1 also? Square root x square minus 1. Where exactly?
Cos inverse x.
Which one?
Cos h inverse x.
Cos h inverse x. And this one we have covered, this one, these two we have covered, this one we have covered, this one. Basically, we have encountered all these four types. Okay?
Yes, sir.
These are not exactly four types. This actually covers minus dx by minus of x square plus a square also. Right? This actually covers that. This actually covers dx by x square minus a square also. Right? We just take negative of it. Right? This
Yes.
covers 2. So basically, this is 2, this 4, this 6, and this one, this is the seventh one. Okay? So
Yes.
basically, these 4 will cover a lot of different types. Okay, ma?
Yes, sir.
Okay. So now here, okay, tell me once again. This one is what? Tan inverse x.
Yes, sir.
Okay, this one is what?
Sine.
Sine or cos? Or sine h or cos h?
Sine h and cos h.
This is x square plus 1 is sine h, x square minus 1 is cos h.
Cos.
Right, this is
For tan.
tan or cot
So
or tan h or cot h.
cot.
This is what? Cot h or tan h.
So tan h.
This is tan h. Okay. You can, in fact, you can write it as cot h also, depending on where the x. If the limits are between this and this, whatever. It depends on whether x is greater than 1, less than 1, right?
Yes.
X is between minus 1 and 1, it becomes tan h, right? Okay, tan h is between x lying between minus 1 and 1. Cot h is when x lying greater than 1. So it doesn't matter. Both are same. What about this?
1 by root 1 minus x square, sir.
This one, 1 by under root 1 minus x square, right?
Sine inverse.
Sine inverse. Okay. Okay. So, but we have so far we have done all of this for x square plus a square, x square minus a square. But uh, the formulas that we have, they are all uh, for the cases where we have ones, right? So, for example, 1 by 1 plus x square, etc. Okay, but doesn't matter. We can do a simple substitution. So, for example, we can take a square common. This becomes 1 by x plus a whole square, right?
Yes, sir.
This integral. Now, if you take x plus x by a as t, what will happen?
X by a is t.
T.
1 plus 1 by t.
Okay, so dx by what we are talking, dx by x square plus a square, right? If you take a square common, dx by a square into 1 plus x by a whole square. Agreed?
Yes, sir.
This is all integral. If you take x by a as t, dx equals to dt, a dt, right? Agreed? So this
Yes, sir.
becomes a dt by a square 1 plus t square. Agreed? So though it is x square plus a square, we convert it to 1 plus x square. So this means 1 by a integral of dt by 1 plus t square. which is again your tan inverse t. 1 by a tan inverse t.
Okay, sir.
Okay? Understood, no? What is your t? T is your x by a. 1 by a tan inverse x by a. So that's why if we know these basic ones, we'll be able to do, we'll be able to write all of this as 1 plus something square or 1 minus something square, right? Just by taking that a square common. Understood, no? We
Yes,
need
sir.
not worry. We need not worry about these a's and all because we can always take that a common and write it as 1 plus something square, 1 minus something square. Okay?
Yes.
Agreed, no?
Hmm.
Okay. So now that's why it is very, very important to remember these formulas. Okay? To remember these formulas, at least now. So now in the ones for yourself, is x square plus a square, x square minus a square, whatever. So we needed this one, we needed this one, we needed this one, we needed this one, right?
Yes, sir.
We needed this one. Okay? This we did not use much.
Hmm.
Okay, we use this. Okay? So
Yes.
that's at least these primary ones you should remember. Ideally, you should remember all of this. Okay. And at the same time, now if you say if you do integrate this, you will get tan h inverse u. Okay.
Hmm.
But most likely sometimes it might happen, you will not be given the option as tan h inverse u. Rather, you will be given an option something like this. So that's why you should be able to recognize then this one. This result and this result are same. Okay, so for example, sine h inverse x you got. Okay, which is nothing but this one.
Okay.
Okay, so if you are given option as this one, you should be able to recognize that this is actually sine h inverse x. So that's why it is important for you to remember this table also. Okay, you have derived this table, right?
Hmm. Yes, sir.
You have derived this table. Basically, whatever we have done, we have derived everything.
Yes, sir.
Right. From where we have derived all trigonometric functions, we derived from basic sine theta plus sine square theta plus cos square theta. From this
Hmm.
kind of relations only, right? Sine h
Yes.
inverse. Okay. Firstly, what we have done, what is our process? We derived, we did the derivatives of sin x, cos x, secant x, tan x, whatever. All six trigonometric functions we did, right?
Hmm. Yes, sir.
First, then what we have using those derivatives we did for inverse trigonometric,
Yes.
right? We assumed sin inverse x equals to y, then we differentiated both times and we express again y in terms of x, right?
Yes, sir.
Now, then what we have done, we have created derivatives of exponential functions, right? E power x. We know
Hmm.
e power x differential is e power x, and we expressed hyperbolic functions in terms of e power x, right?
Yes. Hmm.
E power x, and we derived the identities in hyperbolic function, right? From
Yes,
here
sir.
to identities, from identities to what we have done, again derivatives. Okay, from derivatives, what you have done, inverse hyperbolic derivatives. Okay, so
Hmm.
we went in this in this direction, right? So basically, we started with the basic definitions of trigonometric functions and basic definitions of hyperbolic functions, and we are able to reach all of this. Okay,
Yes.
okay, so we are able to reach this one also. What exactly is sine h inverse and why exactly is this? Okay,
Hmm.
now this is now at the summary we have reached this kind of table, right?
Yes, sir.
The basic differentials of trigonometric and hyperbolic anyway we have, right? This table you have reached, and similarly the regular table for trigonometric functions, right? No,
Hmm. Yes,
okay.
sir.
So now after reaching here, now these fours have become very easy, right?
Hmm.
These four have become very easy in terms of antiderivatives. We did not actually do any integration here. What in these four, just now what we have done, we just said that we know the derivatives, that's why this should be that. We did not actually do any derivative. We did not use by parts, we did not use any substitution, etc. Right?
Yes, sir.
We did not do any derivative. We just used our antiderivatives, known antiderivatives. Okay.
Hmm.
So now, but we have learnt some integration techniques like substitution or by parts and all, etc. Okay. Okay. One
Yes.
more thing. These two are not there. Can you see? These two you will not find. Whatever inverse trigonometric, inverse hyperbolic, all are 1 by something square or 1 by square root of something. All are 1 bys. Right?
Hmm.
All
So
are
for
one base.
that itself, I don't know what the proof is, but for root x square minus a square dx,
Mm.
isn't it? No, a square minus x square, I guess. It is x by 2
Right.
something.
So you know the formula. So your textbook would have given some formula. Okay.
Yeah,
Okay. So
using it he
there are
asks.
some formulas, but we are formulas are good, but we should understand the derivation. Then we can remember the formula. Otherwise, we will get confused.
Hmm.
Okay. Why which formula we are using? It becomes very tricky. Okay, there are formulas definitely. Okay, but ideally we should be able to reach the formulas using the basic definitions. Okay, ma. So
Yes.
that is our attempt here. Okay, all these will have some formulas or
Hmm.
some techniques, but ideally with the least amount of basic knowledge, we should be able to reach all of them. Okay, so for example, entire geometry, like plane geometry, you know, right? Plane geometry.
Yes, sir.
Okay, entire plane geometry is based on four or five axioms, right?
Hmm.
That two lines will meet at one point, or if they are parallel they will not meet. Okay,
Yes, sir.
these kind of statements, these are called axioms, right? Everything
Yes,
else
sir.
is derived. So even for this example, for example, sum of three angles of a triangle is 180 degrees. That's actually derived from the basic axioms, right? Everything.
Hmm.
Okay, so likewise, here also, what is our attempt? To derive everything from the basic definitions, so that at least so that we know exactly where exactly we use what, and at the same time, even if we forget the formula, we will be able to still manage.
Hmm.
Okay,
Yes.
okay. So formulas, they will help us to gain speed, but derivation will help us to gain the thorough understanding of the subject. Okay, ma.
Yes.
Okay, this will have a formula, but interestingly, this and this are somehow related. Okay,
Okay.
just look at this formula and let's see if this has got something related to this. This formula you would have found, no? X square minus a square, square root of x square minus a square, which is there in the numerator.
Hmm. Yes, sir.
What is that formula? Square root of x square minus a square,
Sir, I know for a square minus x square.
square root of x square minus a square. This one. This formula, this one. For this one, you would have found the textbook would have given some formula, no?
Hmm.
What is that formula? X under root x square minus a square by 2 something something it would have given, no?
Huh. Yes, sir.
Uh, so
I'm trying to
some
do.
formula, okay, some formula, okay, just tell me the formula. Some formula, does it involve cos h inverse? Or tell me the complete formula. Complete formula for this one.
For just root x square minus a square.
This integral, they would have given some formula, right? This integral, what exactly is the formula?
Sir, isn't it something like x by root x square minus a square?
No, it is not. This there will be a different formula for this.
Generalized.
No. General, not exactly generally. You would, earlier you were telling me. You are just telling me
That
slightly
one
some.
is for root a square minus x square, right? X by
Oh, okay.
2.
This one. This the second part of this one you are talking about.
Yes, sir. X by
Okay.
2 root a square minus x
Okay.
square.
Tell me. What exactly is that? X by two.
X by 2 root a square minus x square
Hmm.
plus a
Hmm.
square by 2 sine inverse x by a.
Very good. Sine inverse x by a. Okay.
Hmm.
So a square minus x square. So this one and this one are related, right? This one sine inverse x by a is there. Here also sine inverse x by a is there. Agreed?
Hmm.
But you got something extra. Okay. So that was
Yes.
my point also. These everything else are dependent on these ones. Right. Somehow you are able to use sin inverse x by a here, even though it is in the numerator. Okay. We will learn shortly why we are able to get that. Okay, ma?
Yes, sir.
Okay. So before that, now, so far, using derivatives, you are able to do all of this. Okay. Now we'll
Hmm.
slightly use a different technique, that is using integrations only. Okay. Using integrations, how do we achieve this? Okay. There is one very important technique called substitution. Okay, where generally you substitute x equals to something. Okay, generally also you are doing a lot of substitutions, right? Now
Yes,
what
sir.
we do this time, we will use some kind of trigonometric substitutions. trigonometric or hyperbolic trigonometric substitutions to make our things easy. Okay.
Okay, sir.
Okay. Now let us be little careful here. In this case, let's say in this case x can be anything, right? X square plus a square can be anything, so x can be anything. Okay. In this case, x square plus a square, x square plus a square, again x can be anything. In the case of x square minus a square, okay, square root of x square minus a square, what we have to ensure? We have to ensure that x square should be greater than a square, right? X square should be greater than a square. Okay, because that is in the denominator, it should be strictly greater, not just greater than or equal to, right?
Yes, sir.
Okay, in the case of a square minus x square, it can be anything. Agreed? X can be anything. In this case, x square should be strictly lesser than a square, right?
Yes.
Okay, because there is a square root here. Okay, so we have got different types of conditions. X can be anything, x can be less than something, x can be strictly greater than something. Okay, we got these varieties, right? So
Yes.
while substitution, we have to be little careful what we can substitute. Okay, so when x is anything, we cannot substitute something like x equals to sine theta, because what
Yes.
will happen? What that means is you are restricting x between -1 and 1. Okay, so when x is anything, you can substitute x equals to tan theta. Agreed? Why? Because tan theta can take anything.
Yes, sir.
Okay, when x is less than, let's say a, or x square less than a square, or x square less than 1, then you can take x as sine theta or cos theta. Agreed? Now here you cannot take x as tan theta. Why? Because if once you call x as tan theta, then that means x is free and can take any value. But here we are forcing x to be lesser than a square. Okay?
Yes, sir.
So that's why you can choose only the sine theta or cos theta or some function which lies between which is less than 1. Understood, no?
Yes, sir.
So this is the technique that we will follow. Okay?
Okay, sir.
Okay. Now fantastic. Now x square plus a square. Okay? X square plus a square. Now here x can take anything. Agreed?
Yes, sir.
X can take anything. Let's take x equals to a tan theta. Okay? So tan theta, it looks something like this. A times of tan theta will look something like this. It doesn't matter. A times of tan theta will also be between minus infinity to plus infinity. Right?
Yes, sir.
Agreed? So x equals to a tan theta. Why we are doing a tan theta? Because x square plus a square will become what? A square into 1 plus tan square. That is a square secant square.
Yes, sir.
Right?
Yes, sir.
Agreed? Now, a square secant square. What does that mean? A square secant square is in the denominator. Okay. What happens to dx? Dx
Yes, sir.
is a secant square theta d theta, right? Dx.
Yes, sir.
Dx. What happens to the denominator? A square secant square, right?
Yes, sir.
Okay. If you cancel this, what will become? 1 by a integral of d theta, right? This is 1 by a theta, right? Which is what? 1 by a. What is theta? Tan
Tan.
inverse x square, tan inverse x by a. Understood?
Yes, sir.
So how we got? We got by taking x as which, because say ideally what is substitution? Substitution, you want to simplify this one to a known function. Okay. So we want to use this everything together and just simplify to a known function. What is our known function? Integral of d theta is a known function. Okay, we want to reach here. What we have done? And y x equals to tan theta we have, because tan 1 plus tan square is secant square we know. Dx is also secant square we know. Agreed?
Yes, sir.
So that's why we have done x equals to tan theta. Okay. We did not, so because this simplifies tan inverse x by a, it actually simplifies a lot. Okay, that's why we have done this. Okay, 1 by
Yes.
a tan inverse x by a we have got. Agreed?
Yes, sir.
Now, this is our very first function, right?
Yes,
This
sir.
one we have done. Okay. Now without the square root, this one. 1 by a square minus x square. Okay. Or 1 by x square minus a square. Or 1 by a square minus x square. This time what we will do, this you have done as what exactly? Tan h inverse, right?
Yes,
Tan h
sir.
inverse or whatever. So now this one we can actually break this. What is this? 1 by a minus x into 1 by a plus x. Right.
Yes, sir.
Okay. So what we can do is actually a plus x plus a minus x. How much? 2a. Right.
Yes, sir.
So we can write it as 1 by 2a into a minus x into a plus x. Right. Agreed.
Yes, sir.
1 by, so basically what we are doing, we're getting the numerator as 2a by 2a. We are just doing it likewise. Why we are doing this? Because we want to separate this into partial fractions. Okay.
Hmm.
Later you'll learn the techniques about the partial fractions also. How do we separate? Okay. For now we have done this. We can do this now. This
Yes, sir.
converts to 1 by 2a into what is this? 1 by a minus x plus 1 by a plus x. Agreed?
Yes, sir.
Okay, so this you can directly integrate. You remember this, no?
Hmm.
This 1 by a minus x, you will assume 1 a minus x as t, then minus dx is, so this is plus t, minus dx is dt, and this is ln t minus of ln t, which is what we are getting. Okay?
Yes, sir.
You know how to anyway integrate this. You know how to integrate this. Okay? What this
Okay.
become? Log a minus log b. So log a by b. Okay?
Yes.
Understood? So same technique we have used here. Okay, it actually is nothing. X square minus a square is negative of dx by a square minus x square. Agreed?
Yes, sir.
Whatever we got, it should be negative of that, which is this. Okay, ma?
Yes, sir.
Okay, so that's how we have done. We have done this one also. This one, so far we have done these ones without the square roots. What we have done, tell me. In this case, what is the substitution you did? Tan
In
theta. In
Yes,
the
sir.
first case, x equals to tan theta. In this case, what you did? You did partial fractions. You just split it. Okay?
Hmm.
Okay. You just split it, and what you have got? You got log 1 plus x by 1 minus x. Half log 1 plus x by 1 minus x. Or 1 minus x minus 1 something. Which is interestingly our tan h inverse. Cot h inverse. 1 plus x by 1 minus x or x plus 1 by x minus 1. Which is what we initially also we estimated that we should be getting this. Okay, ma?
Yes. Okay.
Okay, so now we have reached this one. What is the third one? This one. Okay, a square minus x square. We have said it is sine inverse x by a. Okay,
Hmm.
it is sine inverse. Where is this? A square minus x square. Sine inverse x by a. But see here, x cannot be anything this time. X has to be less than 1. X, or in fact, x has to lie between minus a and plus a, right? X square is less than a square. What does that mean? X should lie between minus a and plus a. Agreed?
Hmm. Yes, sir.
Right. So, for example, x square less than 4. What does that mean? What are the values of x? X should be between minus 2 and plus 2. Agreed?
Hmm.
Okay, x cannot go beyond 2 or cannot go lesser than minus 2, right? When x square is less than 4. So, x should lie between minus a and plus a. Okay, when you have such a restriction, what is our ideal option? X we will call it as a sin theta because sin theta runs between minus 1 and 1 and a sin theta will run between minus a and plus a. Okay,
Okay, sir.
okay, this is one kind of substitution. Okay, x equals to a square, x lies between this thing, right?
Hmm.
Okay, I think I have. Okay. So this thing is different. Okay. X equals to a sin theta. What will happen? A square minus a square into 1 minus sin square. This is
Hmm.
agreed.
Yes, sir.
Square root of that becomes square root of a square cos square. Okay.
Okay,
Now
sir.
square root of a square cos square is mod a cos theta. Right. Square root is always a positive number. Right.
Yes,
Now
sir.
now can so square root of something here not exactly clear whether we should take it as plus a cos theta or minus a cos theta. We are not exactly clear. Okay. Now something interesting. Sin theta we have taken it from minus pi by 2 to pi by 2. Okay.
Yes, sir.
Okay. This part to this part. Sin can be negative to positive because we want minus a to plus a. But in this region, what is cos? Cos is something like this, right?
Yes.
Sorry. What is cos? Cos is something like this, right?
Hmm.
Minus pi by 2 to pi by 2, cos is always positive, right?
Yes, sir.
Okay, that is secant and all. This cos is actually this graph, right? Okay, minus pi by 2 to pi by 2, cos is always positive. That's why we can freely assume that we don't need this mod. Okay,
Yes.
understood. Otherwise, root of a square cos square cannot directly take it as a cos theta, right? We don't know the inside part is negative or positive. Agreed?
Yes,
Because
sir.
if we are talking about this number, when sin theta is little towards this side, a cos theta could have been negative, right?
Yes,
Sin,
sir.
okay. So that's why, but here, because we are choosing minus pi by 2 to pi by 2, and because we know that cos theta is positive, we can freely assume that this is actually a cos theta. Okay. Now,
Yes, sir.
what is it? Dx by a cos theta. Okay. What is our dx? X is a sin theta. What is our dx?
Yes,
Dx
sir.
is a cos theta again. A cos theta d theta, right?
Yes.
Dx also we have to change, not just the denominator. What is dx? A cos theta sin theta. So both will get cancelled. Integral of d theta, which is nothing but theta. What is our theta? Sin
Same.
inverse x by a. That's why you got sin inverse x by a. Okay, ma?
Okay, sir.
Okay. So basically using the basic techniques where we have reached, we have done this one, right?
Yes, sir.
Using x equals to tan theta. Here, what is the substitution? In this one, it is not substitution. This is partial fraction. Okay.
Fraction.
This one, x equals to a sin theta. Okay. Now,
Yes.
in this case, x square plus a square and x square minus a square is there. X square plus a square. X can be anything. Agreed?
Yes, sir.
In x square plus a square, x can be anything. Okay. In a square plus x square. Okay. X square plus x square, x can be anything. Okay.
Hmm.
X can be anything means what you can take, like the earlier case, x you can take it as tan theta. Okay. If you
Yes,
take
sir.
x as tan theta, what will happen? X square plus a square tan square plus a square, a secant theta. So dx equals to a secant square theta. Agreed, you have got this one. Dx
Yes.
is a secant square theta and under root of x square plus a square. Okay. And this is again under root of a square into 1 plus tan square, which is under root of a square secant square. Okay.
Okay.
Fantastic. But again, here also, it should be a secant theta mod. It is not directly a secant theta, right?
Hmm.
Okay, but here also the same thing. When tan theta between minus pi by 2 to pi by 2 is what we are choosing, right? And
Yes,
we
sir.
just discussed between minus pi by 2 to pi by 2, cos theta is also positive. That's why secant theta is always positive, right?
Yes,
Because
sir.
we know secant theta is always positive, we are ignoring these mods. Okay, that's why we are able to write it as a secant theta. This is important. Okay, Amma? Why we are writing it as a secant theta and but not this one? Okay.
Hmm.
Now you know this, you are actually cancelling, you got integral of secant theta. But you know integral of secant theta, which
Hmm.
is log of secant plus tan. So this time we are using this mod. Okay, because we don't know.
Okay, sir.
Okay,
Yes, sir.
okay, log of secant theta. Now this one, how did we get? We substituted tan theta equals to, this is theta, tan theta equals to x by a, right?
Hmm.
Theta, what did we substitute? X equals to a tan theta, right?
Yes, sir.
So tan theta equals to x by a. Okay, opposite by adjacent. Okay, what will become of hypotenuse? X square plus a square square root, right?
Hmm.
So now what will become of secant theta? Root of x square plus a square by a, right?
Yes, sir.
So what we have got? Log of secant theta. So it is log of root of x square plus a square by a plus tan theta, which is x by a. Agreed?
Yes, sir.
Okay, so what has it become? Root of x square plus a square plus x whole by a. That's why we are getting this. Understood?
Hmm.
Okay?
Yes, sir.
Okay, this is by substituting x equals to a tan theta. Okay, this is an easy substitution for us because we know tan theta is minus infinity to plus infinity and x is free to take any number. That's why we are choosing this. Okay, there is
Hmm.
another way of choosing. Okay, you remember sin hx. Okay, the original graph of sin hx.
Hmm.
Okay, where is sin hx? This also runs between minus infinity to plus infinity, right?
Yes.
Okay, so you can actually take this function also, right?
Hmm.
Minus infinity to plus infinity. So let us try doing that also. Where is this? This one. Okay. Here you are taking x as a sin hx, sin h theta. Okay.
Hmm.
We can take this, no, because x can take any value. That's why we are taking a sin h theta. So what will become of this? A square plus a square sin h square. A square into 1 plus sin h square. 1 plus sin h square is cos square, cos h square, right?
Yes, sir.
And cos h square, that is also always positive. That's why we are not able, we don't need to worry about this mod. Okay.
Yes,
So,
sir.
and what will happen to dx? If x equals to a sin h, dx is a cos h. Okay. So both will get cancelled. We simplified to directly theta. In this case, we got secant theta. Earlier, for the regular ones, we got integral of direct d theta. No. So
Hmm.
similarly, if we take this kind of substitution, we are directly getting theta. What is our theta? Sin h inverse x by a, right?
Yes, sir.
Sin h inverse x by a. And you know the formula for sin h inverse, which is nothing but this. Which we got the same result. Okay, ma?
Hmm.
Okay, a square plus x square. Either you can substitute x equals to a sin h or x equals to tan. It doesn't matter. As long as you are free to take x as any value, that's why we are choosing this function. Okay.
Hmm.
So why we choose which function is actually very important. We cannot take x equals to a sin theta, right? We
Yes,
cannot
sir.
take x equals to a cos theta because x is free to go anywhere here. Okay. That's
Hmm.
why we are choosing tan theta or secant or sin h. Okay, if we choose, if you remember this formula, right, sin h inverse. Okay, then you can directly take a sin h. But if you don't remember these formulas, you can choose this way and still be able to reach using the basic trigonometric identities. Okay,
Hmm.
okay, we just drew the right angle triangle and derived these ones. Okay, ma. But
Yes, sir.
ideally, you remember this formulas also because in our option you might be given this or this.
Okay.
Okay. Okay. Next, so what we have covered? We have covered x square plus a square. Okay. What is left? Only x square minus a square, right?
Yes, sir.
Okay. X square minus a square. What does that mean? X square should be greater should be greater than a square. Okay. X square greater than 4. What does that mean? What is the values? What are the values of x? X should be greater than 2 or x should be less than minus 2, right?
Hmm. Yes.
This one we have done. Oh, no, no, not this one. X square, where did we? X square minus a square. So x square greater than 2 square. What does that mean? X greater than plus 2 or x less than minus 2, right? Because it's in the denominator. We are not taking equal to. Okay, ma?
Yes.
Okay. X square, x greater than, let's say a. Okay.
Yes.
Okay. X is greater than a. So that means x you can either you can take x as secant theta. Okay. So x, if you take x as secant theta, x square is secant square a square into secant square minus 1, right? Which you will get at a root of tan square. Okay. That way also you can go. You can take x as secant theta, then dx will become what? Secant theta tan theta by tan theta. So integral of secant theta you'll get, and still you'll still be able to differentiate, or you'll still be able to do this one. Log of secant plus tan, you'll get the same result. Okay,
Hmm.
understood? If you take x as secant theta, understood, Amma?
Yes, sir.
Okay, or other way, x is again greater than 1. X you can take is as cos h. Okay, in this case, cos h is taken. Why cos h? Because cos h is always greater than 1. Okay, remember the graph now?
Hmm.
Cos h is always greater than 1. Okay, secant x is also always greater than 1. Either you can take secant x. Okay, if you take secant x, you will restrict between minus pi by 2 to pi by 2. If you take cos h, you can take anything. Okay, ma?
Okay.
Understood. So in this case, what is the substitution we do? You can choose either. Okay. Now here he is done with cos h. You do with secant h and still be able to get the same result. Just do it. Okay, ma?
Hmm. Yes,
Understood
sir.
this? Understood?
Yes, sir.
Okay. Now you tell me the summary. What all we have done in this. to get these four?
First one, tan x, tan inverse x we substituted.
No, no, x equals to tan theta, a tan theta.
X is equal to a tan theta.
X equals to a tan theta we substituted. Very good.
Then third one we did partial differentiation.
Third one, partial fractions. Very good.
Fraction.
Uh,
And then fourth one, substitute a sine
a
theta.
sin theta. Why? Because x should be less than a.
Yes, sir.
Next one, this one, x square
Same
plus a square.
a cos.
A cos for which case? For the second case, when x is
Second.
greater than a. Okay?
Hmm.
When x can be anything, we again did tan theta
Partial.
or sin hx.
Tan
Okay?
theta sin x. Yes,
Or
sir.
sin hx. So when x can be anything, you can choose tan or you can choose sin h.
Hmm.
Okay? When x has to be greater than 1 or greater than a, you can choose secant or
Cos.
cos hx.
Hmm.
When x has to be less than 1, we can choose sine. You can choose cos also, but sine is easier for us, right?
Hmm.
We can choose any function. Okay, but whichever ones we are convenient with sine, we are convenient with secant and tan, we choose those functions. Okay,
Yes.
agreed. Okay, now coming to this one. Okay, so these four are covered. Okay,
Hmm.
coming to a square plus x square, a square minus x square, and x square minus a square. Okay, a square plus x square, a square minus x square. X has to be less than a. Okay, so x you can take it as sine theta. Agreed.
Yes, sir.
Okay, so this becomes what? What is dx? A cos theta d theta. You are getting this one. Okay,
Hmm.
this is a cos theta, this is a cos theta. Cos square theta, now you know this is known this one region, right? Cos square, 1 plus cos 2 theta by 2, right? This is
Yes.
d theta plus cos 2 theta, which is sine, this one right? Okay,
Yes.
so this you can further simplify 2 sine theta cos theta. Okay, what is our sine theta? What is our initial substitution? This is theta. Okay, x equals to a sine theta. X by a equals to sine theta. Okay, if this is
Yes.
your theta, this is your x, this is your a, right? This
Hmm.
becomes your a square minus x square, right? So what becomes your theta? Sine inverse x by a. Agreed. What is your sine theta? Sine theta is x by uh, what is sine theta? X by a, right? Sine theta
Yes,
is
sir.
x by a, which is this one. What is our cos theta? Root of x square minus root of a square minus x square by a. Root of x square minus x square by a. Root of x square minus a square by a. Okay, ma?
Hmm. Yes, sir.
Okay, this is this only. Root of a square minus x square by the square root you can keep in the top and denominator you will get this. Okay, ma?
Yes.
Okay, so what will become of this? If this a square is anyway outside. Okay, so we are just multiplying this and we got this. I think this is the formula that you are telling, right?
Yes.
Okay, this is this in this case what you have done? X equals to a sin theta is what we have done. No, no, no. X equals to a sin theta. Agreed?
Yes, sir.
Okay, so this is one way of doing. Okay, another way of doing is using our another method, which is our by parts. Okay, what is our by parts? We take this first function and we take one as the second function. Okay, then So you take the first function, root of a square minus x square. You take the first function as 1. Okay, then first function into integral of second function, that is x. Okay, minus differential of first function. What is that? A square minus x square. This becomes minus 2x. Okay, that is differential of first function into integral of second function. Okay, integration of this. Okay.
Yes.
Okay, what becomes this? This becomes this 2 and this 2 will get cancelled. We are getting x square by under root a square minus x square. Okay,
Hmm.
this minus and minus will become plus. Basically, this thing plus integral of x square by under root a square minus x square dx. Agreed?
Hmm.
Okay, or let it be minus and minus only. Okay, agreed? This integral minus uh, x minus x square by under root a square minus x square. Okay, here what we do, for this we will add 1 a square and we will subtract 1 a square. Fine.
Hmm.
Okay, so this entire piece is as is minus integral of, if you take the first piece, what you get? Under root a square minus x square dx. Okay? Minus, this minus into minus will become plus, plus integral of a square by under root a square minus x square dx. Right?
Hmm.
Okay. So this entire thing should be equal to this one, right? If the
Yes.
original one I is this, I equals to something minus again I, right? This is equal to this only, right?
Yes,
I
sir.
equals to something minus I plus this one. This one you know. This is a square sine inverse x by a, right? This
Yes,
one you
sir.
know. Okay, this one you know. So what is saying? This I equals to, or he is calling this a. A equals to something minus again a plus a square sine inverse. Okay, so a plus a will become 2a or 2a or 2a. 2 times of integral of this is actually equal to this. So integral of this is actually equal to half of this one. That's how you got this. Okay.
Yes.
So here what did we do? We expressed this again in terms of this. That is the technique we have used. We didn't actually integrate anything, right? Did we
Hmm.
integrate? We
No,
didn't.
sir.
We didn't actually integrate. What we have done, we have broken this integral into parts such that this is expressed in this in itself. Okay.
Okay.
And what we have done, we have cleverly used plus a square minus a square. That is the trick here. Okay, ma?
Yes, sir.
Here we have done using by parts. Okay. And why we have done using by parts? And what helped here? This also we used. This also helped. If we don't know this, then we cannot do by parts, right?
Hmm.
Sine in this we should know this is equal to sine inverse x by a. Okay. So that's why it was actually dependent on sine inverse x by a. Right. 1 by under root 1 minus x square. Right. We were discussing earlier, no? Why we got sine inverse x by a in this integral. Right.
Yes, sir.
Okay, so because it is like this, we got this. Okay, so now we have learnt two ways of doing this. One is substitution. Okay, you might feel this is slightly easier. Okay,
Hmm.
okay, because substitution generally people feel substitution is easy, but if you do little practice, this also will look easy. Okay, integration by parts is a powerful technique.
Yes, sir.
Okay, okay, substitution. Some people will get confused where to substitute what, whether to put sine theta, cos theta, they get confused. Okay, but
Hmm.
you don't have that confusion because you know when to put what. Okay, now uh, here by parts also you can do. Okay,
Okay, sir.
but by parts is this kind of technique is interesting because in lot of cases where substitution doesn't work, no, this technique will become important where you want to express this integral in itself only. Okay, ma.
Hmm.
Okay. Now this one, x square minus a square. What can we take x? X should be greater than a. Either x you take as secant theta or x you take as cos h theta. Okay.
Yes.
If you take the cos h substitution, you are getting this. Okay. This becomes a square sine h square. And you know, you established already the identity sine h square in terms of cos 2h. Okay.
Yes, sir.
Sine h 2 theta also in terms of sine h and cos h. You have done this. Okay.
Yes, sir.
Agreed. Okay, so and because you know the identities, you are able to express everything in this form. So ultimately, you got this result. Okay, this is using hyperbolic substitution. Again, using by parts. Okay, again, what you have done? First function into second function. Right, first function into integral of second function minus integral of differential of first function into integral of second function. Again, x square by under root x square minus a square. This time you are adding a square and minus a square. Okay.
Hmm.
Again, I becomes I some I. Okay. Because this is equal to I. I equal to something minus I minus a square into this. This is a known function cos h inverse. Right.
Yes, sir.
Agreed, ma. So 2I becomes this minus this. Okay, I becomes this by half. Agreed? Same technique we used in this. Okay, in this, the water technique we have is exactly the same technique.
Hmm.
Okay, ma?
Yes, sir.
Okay, now we are left with this is only the final one. Okay, a square plus x square. X can be anything. If x can be anything, you can either take x as tan theta or you can take x as sin h. Okay.
Hmm.
Agreed. If you do the substitution and you do something similar like this, you will get the answer. Okay, just do it yourself. Okay, all of this. Okay,
Yes.
or otherwise you can do the by parts method also. Okay. by parts again, first function integral, second function, etc. Plus a square minus a square you will do again, and you get again I in terms of I. Okay, and you got this result. Understood?
Yes.
Okay, so we have covered all these basic functions. Where are these basic functions? In your syllabus, we have covered this, and this. Okay,
Yes. Yes.
okay, all of this. But what you have to do, all of this using antiderivatives you should do. All of this using substitution you should do, and all these things using by parts also you should do. Okay.
Okay.
In substitution you do substitute using sine theta, secant theta, sorry, tan and sine h, as well as uh, secant and cos h. Okay, do both
Yes.
kinds of substitution, you still be able to get the same result. Okay, do
Okay,
all
sir.
of this today once again. Okay, ma?
Yes, sir.
Okay, and at the same time, all the six trigonometric functions. Okay,
Yes, sir.
okay. What you should thoroughly always remember is all six trigonometric functions. Okay,
Hmm.
their graphs, their derivatives. Graphs means including domain range. Okay, and the look and feel of the graph. Okay, their six trigonometric, six inverse trigonometric. Okay, their graphs, all of this, their graphs, their domain, their range, and their derivatives also. Okay,
Yes.
and their derivatives at the same time, all your hyperbolic trigonometric functions. Okay, their graphs, hyperbolic and inverse hyperbolic. Basically, 6 plus 6 plus 6 plus 6. These 24 graphs, derivatives, you should know.
Yes, sir.
Okay, and at the same time, this sine h inverse, all these six inverse functions are there now to be able to express in terms of the regular functions. Okay,
Hmm. Okay, sir.
okay, and at the same time, the identities, sine h square, cos h square, whatever. Okay, establishing the identities. So basically,
Hmm.
what I'm trying to say is this table you should be able to thoroughly remember and derive. This one you should be able to thoroughly able and remember, to derive and remember. Okay, ma?
Okay, sir.
Okay, so the more you do these things, okay, these graphs you will forget now, because now we will remember, otherwise you will forget. Okay,
Hmm.
you keep revising this, then this entire integration will become very easy. Okay, so now that you know these six ones, okay, 1, 2, 3, 4, 5, 6. In fact, these two are also dependent on the top four only, and these are also dependent on your antiderivatives only. Okay,
Okay.
the rest we have only 1, 2, 3, 4. These four are actually pretty straightforward, which I will tell you. Okay, so this is what you are given specifically in our JE syllabus, right? We
Hmm.
have other things also, so we can go little deeper in the other cases also. For example, here he is saying integration of simple functions, somewhere something like this. Evaluation of simple integrals is saying, right? What is simple? This is kind of little dicey, right? So what is simple for you may not be simple for someone else. So that's why we'll go little deeper here also. Okay, integration by parts, different varieties of problems we will do. Okay.
Hmm. Fine, sir.
Okay, and we need to know what exactly is fundamental theorem of calculus, what are definite properties of definite integrals, then determine regions, etc., etc. Okay, ma. So we'll do all of this. Okay, so now today you continue practicing that. Okay, you have sent me these ones, no, the types of questions.
Fine,
The
sir.
questions you sent me the questions that you are doing, no, in our
Hmm.
case.
Hmm.
Okay, just finish off that entire exercise then. Your case at your board and all.
Fine, sir.
Okay, all questions you should be able to do now. Okay, what will be left with some kind of reduction questions? Sine power n, cos power n, sine power m, cos power m. These kind of reduction questions you might not be able to do,
Hmm.
but otherwise most of them you should be able to do. Okay, we will
Okay.
discuss about how to do reduction formulas also.
Hmm.
Okay, ma.
Fine, sir.
Cool then. Take care. All the best.
Thank you, sir. Bye,
Okay,
sir.
bye bye.